All right, should I start? William?
Yes, go ahead, please.
Okay, thanks. Yeah, so thanks for inviting me to speak here today and to participate in this workshop. For those of you who don't know me, I am Francois Foucart, and I'm currently at the University of New Hampshire. I mostly work on numerical simulations of black hole neutron star and neutron star mergers with the spec code, which is developed by the SXS collaboration. So first out of Cornell and Caltech for the binary black hole code. And over the years, we have added fluid dynamics, magnetic fields, neutrino transport, and so on, mostly with my collaborator at Due and myself. So for this talk, we were asked to give some recent results in numerical relativity, and I chose to focus specifically on our efforts to model the mildly relativistic outflows coming from neutron star, and black hole neutron star mergers. So the outflow responsible for the production of kilonovae and the production of R process elements and the enrichment of the universe in heavy elements, assuming that, of course, neutron star mergers are the main source of that enrichment, which is not certain at this point. So to model kilonovae, the main role of numerical simulations, in my view, is to just give a good idea of what the properties of the matter ejected by the merger is as a function of the parameters of the binary, the masses and spins of the merging objects, and the input physics, such as, most importantly, maybe the equation of state of the neutron stars. And so we want to get a good idea of what the mass, energy, composition, velocity, and geometry of these outflows are in order to connect these masses, spins, equations of state to kilonova-like curves and be able to make inferences about these objects from kilonovae observations, and also in order to predict the outcome of our process nucleosynthesis in these mergers. And that's the role of merger simulations, but that's of course not the only part of the problem. There is an entirely other part I'm not even going to talk about today, which is everything that happens after the matter is ejected, which is usually treated with photon transport code with complex nuclear physics questions involved. And that has an entirely different type of uncertainties that I'm not going to touch on, but that are good to keep in mind. But what I want to emphasize in this talk is that just looking at what the merger simulations can tell us, there is already a fairly large amount of uncertainty in our predictions for the outflows. The current models are, in my view, at best order of magnitude accurate, limited by a number of things, including the computational cost of simulations and the limited physics that is currently included in many simulations. And I'll come back to that in a minute. And also the lack of parameter space coverage of the pretty large space of black hole neutron star and neutron star binaries, at least with simulations that have sufficient physics to model all of these properties of the ejector. Particularly, the composition can be tricky if you do not have a good neutrino transport, as we'll see. Okay. So the main issues that we are facing, I think, in terms of implementing physics into these simulations have to do with neutrinos, which I'll come back to in a minute, and probably small-scale instabilities in these mergers. The most problematic being, in my view, the Kelvin-Helmholtz instability that is present in the shear region between two merging neutron stars, as well as, for example, at the interface between a forming disk and a tidal tail. And the role of this instability is shown, for example, in this movie by my graduate students, Sasha Chernoglazov, who is currently at UNH. This is a horizontal slice through a neutron star merger, with on the right the density and on the left the magnetic energy, both on log scales. And you can see the growth of the Kelvin-Helmholtz instability in this region in between the two cores, particularly on the magnetic field plot, not so much on the density. And that instability grows for as long as the two neutron stars are rapidly orbiting each other, and you get a significant shear between the two cores. But you can see that it grows on very small scales. This is a simulation with a resolution of about 150 meters. which is fairly typical for merger simulations today. Now, the problem is that, as many of you know, at that resolution, you can only capture the growth of that instability to its saturation level if you start with an unrealistically large magnetic fields. And you're going to see as this simulation progress that, in fact, the magnetic field that grows from this fluid instability is actually going to dissipate over time in this simulation, not because we expect it to do for physical reasons on these timescales, but simply because of numerical dissipation in the simulation. This is a problem in this simulation, but this is generally a problem in all simulations performed so far. The highest resolution simulation performed by Kenta Kiyushi, which is an order of magnitude smaller grid spacing than in this one, still does not converge to a well-defined value for the magnetic field after merger. And that is important for a number of reasons. One is that these instabilities are responsible for heating the remnant and transporting angular momentum through the remnant. And the other that the fact that we cannot fully resolve magnetic fields in these simulations means that we cannot predict what the large-scale structure of the magnetic field is after a merger. We can set a magnetic field like a dipole in the neutron stars before merger at maybe 10 to the 9, 10 to the 10 gauss or something like that. But then it's going to grow to those 10 to the 16-ish gauss during merger. And we know that we can grow that on small scale, but whether there will be some sort of dynamo effect that will create a larger scale field or not, what the form of that field will be, all of that is something that simulations cannot predict at this point. And we will see that that has an important effect on outflows. The second physical process that we would like to properly include in simulation, but that many simulations at this point do not sufficiently well model, is neutrino transport effects, which we talked a lot more about yesterday. The general idea is that neutrinos are responsible for cooling the disk and the remnant. They may drive outflows from the disk and from possible neutron star remnant. Also, typically, this seems to be, at least at early times, subdominant when compared to magnetically driven outflows. Quite importantly, neutrino absorption and emission is going to change the composition of the outflows, which we usually characterize by the electron fraction YE. This is shown, for example, on this plot here. The different contours here in a vertical slice through a neutron star post-merger remnant shows the density. So this is the core of the remnant, which is very neutron rich, electron fraction of less than 10%. It's surrounded by an accretion disk, which is a little less neutron rich, 15, 20% protons or so. And then in the polar region here and here, you get outflows, which due to neutrino emission and absorption are typically at a much higher YE. And that is crucial if you want to properly predict the properties of kilonovae, the duration and magnitude and color of kilonovae, as well as the outcome of our process in these systems. And that change in the electron fraction in the outflows is only captured if you properly include neutrino transport and absorption in your simulations. For most of the other aspects of neutrinos, absorption is not so crucial, but for driving winds and absorption and changing YE, having proper neutrino transport is really important. So we've already heard a little bit about neutrino transport yesterday. I'm going to emphasize again the point that Josh already made yesterday, that one potential avenue to go from the approximate method for neutrino transport that have been used so far to fully solving Boltzmann's equations of radiation transport is Monte Carlo methods. Josh's group has already done Monte Carlo simulations for post-merger remnant accretion disk. And Monte Carlo methods have been used in the supernova community as well. But I can tell you that we can also now do this for neutron star mergers at a cost that is fairly comparable to our two-moment scheme, which arguably is a pretty expensive two-moment scheme compared to what many people are using. But that corresponds to about a factor of 2 increase in the cost of the simulation for us compared to a fluid simulation. Here's what we are currently looking at. It's a vertical slice through a neutron star merger again, where you see the density on the right and the composition, sorry, the density on the left and the composition on the right. And I'm going to pause late in the evolution here as we form a wind here. You can see that at this very low resolution, I mean, this Monte Carlo simulation is set up to be as cheap as possible. You can actually see very close to the surface of the neutron star the effect of shot noise from Monte Carlo in these small scale oscillations in the composition. But as you get farther away from the neutron star and interactions with many neutrino packets kind of average the effect of neutrino absorption and emission, you see that the outflows are a lot smoother, not only in density, but also in composition. And we are doing conversion tests with different number of packets and also finding that even at very low resolution, we actually get pretty decent results. Now it's very preliminary, and there is certainly a lot more to do to make these methods more robust and to test them in more details. But I think that's a very promising avenue, at least for neutrino transport. And that leads me to say that, in my view, the first problem, the small scale instabilities, is something that is really difficult to solve right now, and that we are still pretty far from fully solving in simulations. While I think the second part, the neutrino transport, is something that we are getting much closer to having a good solution for and to be able to implement properly in many simulations. So I think this is going to be a lot easier to make progress on in the next few years. All right. So that's what I wanted to say about the physics that we need to include in the simulations and the current main problems, at least in my personal experience. For the rest of the talk, I'm going to look more at how that translates into what we can and cannot do in terms of modeling the outflows that power kilonovae and our process nucleosynthesis. And many of you have probably seen this plot by Dan Kaysen and collaborators showing the diversity of outflows that occur in neutron star, and black hole neutron star merger. The important thing being that there is 5, 6, 7 different types of physical mechanisms that can drive outflows. All of them come with different properties, have different uncertainties in the amount of mass that is ejected and the composition and velocities and so on. And that's what really makes modeling this whole problem difficult, but that's also what makes it interesting, because different binaries will have different ratios of these types of outflows, leading to different types of kilonovae. And so that's why we can actually hope to extract information about the merging combined objects from the observation of kilonovae. It's because the different systems are going to give us such different answers. All right, so what can we say and not say about these outflows at the moment? I should say that everything I'm going to say now reflect probably some of my biases having done some of these simulations, but I try to be cautious about what I think we can and cannot say at this point. We can certainly have a discussion about that, about what might be inaccurate there later. So for black hole neutron star, I think the ejection that comes at the times of merger is probably the part of the matter ejection that is best understood at this point. So if you have black hole neutron star system, in the case in which the neutron star is disrupted by its black hole companion, we can fairly accurately predict within about 10% what the mass of the ejected material is, and that was done by Kohei Kawaguchi first, and we recently provided an update to that formula with Christian Kruger. We also know the property of that ejecta very well because it's actually very simple. The velocity is well modeled by Kohei Kawaguchi's paper. It is always very cold and neutron rich, so there is very little uncertainty on what the outcome of nucleosynthesis is going to be, or I should say that all of the uncertainties about the outcome of nucleosynthesis have to do with nuclear physics and not merger simulations. And it can be a pretty large amount of mass, a few percent of a solar mass, certainly, if the neutron star disrupt. The difficulty here is that many black hole neutron star merger do not lead to the disruption of the neutron star. It really only happens if you have a low mass black hole, a highly spinning black hole, and or a large neutron star. And that's something that is shown in these papers, as well as in some of the predictions for the remnant disk mass that are produced by black hole neutron star merger that I have done over the years. Some examples are shown here as a function of mass ratio and radius, showing all of the black regions here, which cover a pretty large part of the parameter space, even for these relatively large black hole spin of 0.5 and 0.75. There is no matter ejection in those regions. And there's also no disk formed, so no post-merger ejection, or at least no significant post-merger ejection in these systems. So black hole neutron star tidal ejecta is fairly well understood, but in many systems will not even exist. Then we can move to the neutron star system, which is always a little bit more complicated. It also has what we could call a tidal ejecta similar to black hole neutron star merger. You can see it particularly in this asymmetric system at the bottom, with binaries of different masses here, where the tidal tail can be clearly seen is going to lead to up to about 1% of a solar mass of matter being ejected. While in an equal mass system shown here, there is very little tidal distortion of the stars and a little mass ejected through that mechanism. Otherwise, the properties of the tidal ejecta in neutron star system is fairly similar to what we find in black hole neutron star system. It is only lower masses because neutron star systems are typically more symmetric in mass than their black hole neutron star counterpart. At least we expect them to be. And that is what leads to lower mass ejection, not any difference in the physics of the process. So this is qualitatively well understood, but there is no clear quantitative model for how much matter is ejected by this process specifically. The second type of merger that comes at the time of the, within a few milliseconds of the merger of the neutron star is what I would call here a co-bonds kind of merger, sometimes called shocked ejecta. It comes from the fact that as the two neutron stars collide, if they do not promptly collapse to a black hole, they are going to experience one or multiple co-bonds, and during that process, during these oscillations, a significant amount of matter can be ejected. Again, from a few times 10 to the minus 3 solar mass up to maybe 1% of a solar mass or so. But the properties of the ejecta here becomes more interesting because this material is much hotter, and so it's going to emit and absorb a lot more neutrinos. And that drives the electron fraction of the ejecta to a significantly higher value, sufficiently high that it is going to modify the outcome of nuclear synthesis and the properties of kilometer. This was first shown by Wanajo and collaborators, thanks in part to the first simulations with good neutrino transport performed by Yushiro Sekiguchi and the Kyoto group. So again, we have, in this case, a fairly good qualitative understanding of what is happening, that if the system immediately collapses to a black hole, there is no ejection through that process. And otherwise, typically more compact star, which are shocked more strongly, leads to more matter ejection through this process. So that is typically what has been observed in simulations, qualitatively. In terms of quantitative models, which we would like to have if we want to make a kilonova model for these neutron star mergers, there's only a few fairly inaccurate models, and I say that including the one that I derive, for the dynamical ejecta of neutron star mergers, which includes both of these components, which again have very different properties. One of them is very neutron rich, the other one is not. They are going to lead to completely different types of kilonova. But yet we only have approximate models for the combination of these two, and they are only correct to about 30–50% accuracy. The first one was probably the one by Tim Dietrich and collaborators, and more recently we derived an updated one with Christian Kruger, and I think at this point there are a few others in the literature. What do we need in order to go beyond that? If we want to improve on these models, well, the main thing is that we need many more simulations covering the parameter space of neutron star binaries, which not only can predict the ejecta, but also have sufficiently good neutrino transport to reliably predict the different components, the different YEs in the ejecta, the different electron fractions. And at this point, that is really the main limiting factor. There is no point making fitting formulae if you only have 4 or 5 good simulations at your disposal. But I think that that is perfectly feasible within the next few years, because we know have quite a few codes that can capture neutrino interactions at the level required for this kind of work. And so I think that this is going to be possible very soon to improve on these models. All right. So for the rest of this talk, let me move to what happens after merger and the longer post-merger evolution, which continues for a few seconds after the merger. The first thing maybe is something that David already talked about earlier in this workshop, that we have to model somehow angular momentum redistribution in the merger remnant to get from these merger simulations which have very asymmetric and sharp merger remnants to the more standard quasi-axisymmetric disks around the black hole or neutron star that are modeled by groups following the post-merger evolution. And the main problem here is the lack of resolution of these small-scale instabilities, which means that we have to rely on subgrid model, including probably the most accurate one developed so far by David Radice and collaborators, which is shown here and shows that in terms of mass ejection at the time of merger, these viscous effects, angular momentum transport effects in the post-merger remnants on short time scales is not going to be probably a dominant effect, but it is of course crucial if you want to properly model what the structure of the post-merger remnant is, because you need to properly transport angular momentum to form a uniformly rotating neutron star surrounded by a accretion disk in quasi-equilibrium. So that's the first problem, is how do we connect these merger simulations to the more long-term evolution of post-merger remnants if we have to rely on subgrid models to do that? How can we calibrate them better? And David has a lot of work on that, and I think we certainly need to look more carefully at what we mean by the mass remaining outside of a black hole or a neutron star after the merger. Because as we will see, that's what all of these post-merger simulations use as their initial conditions. And if we cannot connect the mass of the disk used in post-merger simulation to what numerical relativists during the merger define as the mass of the disk, we can't actually build a reliable model as a function of the input parameters of the system. More briefly, because I've assumed that Daniel will talk a bit more about that later. We can also see two broad type of outflows on the second time scale, which are very important and might be the dominant types of outflows in all of these neutron star systems. One is due to angular momentum transport due to the magnetorotational instability in the accretion disk, occurs on second time scale, and so far has been mostly studied through 2D simulations using alpha type viscosities. But these simulations have been tested against a few seconds long 3D MHD simulations, and there is reasonable agreement between the two methods. What is found is that between 5 to 25% of the mass of the disk against that equilibrium idealized disk used in these post-merger simulations, 5 to 25% of the mass of the disk is ejected, which can be a significant amount of mass, certainly comparable or larger than the dynamical eject. And that viscous outflow is typically very slow, a few percent of solar mass, and can be at much higher YE than the tidal ejecta. But for that part is a little uncertain, because these long post-merger simulations have to make some trade-off on the amount of physics that they include to be able to evolve for 5 seconds or so. And so the neutron transport is not as developed as in the best merger simulations. And the second important type of outflows, and maybe the most uncertain in these post-merger disks, it comes from magnetically driven wind in the second time scale following the merger. That was studied in merger simulations by Kentaki Yushi and collaborators, and in post-merger configurations first by Daniel, and more recently by Rodrigo Fernandez and Sasha Tchaikovsky's group. And then with full radiation transport with Monte Carlo method by Jonah Miller and the Los Alamos group. And what these simulations show is that on much shorter time scale, you can have a faster ejecta component, which is driven by magnetic fields again, and which is strongly dependent on the structure of the magnetic field in the post-merger remnant. This is shown on this plot here on the right, where you see the mass ejected in the simulation by Ia and Christie for different magnetic field configuration, whether it's poloidal or toroidal, effectively, in this case. And the purely viscous simulations, the late time outflows, already show ejection of matter at the level of 25% of the disk mass. And then you can raise that from a few percent more to nearly twice that if you include MHD and the early times outflow on a less than a second time scale. And because we do not know what the structure of the magnetic field is after a merger, this part of the outflows is very, very uncertain. It could be nearly zero, or it could be as much as the viscous outflows. And I think that that's one of the most important limitations of our current attempts to model Tidal signal, is that there is that huge uncertainty on the amount of outflows that come from the post-merger disk that is going to be related to what is the structure of the magnetic field after a neutron star or that neutron star merger. Okay. I'm running a bit out of time, so I'm not going to talk too much about what happens when you have a neutron star at the center, but as a summary, you typically end up with more neutrino emission, a higher YE in the outflows, and there aren't too many long-term simulations of these systems at the moment because it's harder to do with the fixed metric simulations. But that's certainly an important question to ask also, is what happens when you have a neutron star, and how can we simulate the neutron star and the disk together in general relativity for long enough timescales. But to conclude, I wanted to show you this plot, which is asking a relatively simple question. This is work by incoming graduate students, Amelia Henkel. If you are trying to see which equations of state are compatible with a certain measured total ejected mass, let's not even get into what the composition of the outflows is or anything like that, or the geometry, just the total ejected mass. So one of the simplest questions that we can ask. To do that, we have to choose a model for the amount of mass that is produced in the accretion disk for a neutron star merger, and how much of that mass is actually unbound in kilonova producing outflows, which in this case we choose to be 10 to 50%. You can argue with these exact numbers, but that's the order of magnitude of the uncertainty. And we consider three models, and I don't think any of them is particularly better than the others at this point. They're all fitted to the same kind of numerical simulations and all suffer from the limited number of data points that we can use to fit the models. The important point is that if you look on the right, these are all of the equations of state allowed by GW17 with 17. And the dark purple ones, which are very few and on the right here, are the equations say that all the models agree could produce 5% of a solar mass of ejecta. All of the other colors, there is some disagreement between these models. Some of them predict that it's possible, some of them predict that it's not. And this really shows that with our current understanding of what the disk mass after the merger is, and current understanding also of how much of that mass is actually ejected after merger, the inferences that we make about the equation of state, for example, of neutron star from the observation of kilonova are going to be very model dependent. And we really need to do better than this if we want to constrain the equation of state to even 1 kilometer using kilonova. And I'm going to stop here and take any question that you might have for me.
Thank you very much. So we have time for questions. Okay, David.
Thank you for a really nice presentation. I have a question about the Monte Carlo transport. Are you using full frequency dependent opacities for these calculations, or are you using gray opacities? And in both cases, how important is it to have good resolution in frequency space with these Monte Carlo packages?
So the Monte Carlo simulations that I show used 16 energy bins for the table, ranging from 0 to 500 MeV. What I should have thought about and didn't initially the first time I ran this with less energy bins is that you actually need to go to pretty high energy because the center of the remnant gets to 50, 60 MeV. which means that the average energy of the neutrinos in your system is actually of the order of 100 MeV, even if the neutrinos that escape the system are actually more in the range of 10 MeV, 20 MeV. So you need a pretty wide range. I haven't done tests at the moment with more or less energy bin. This is the first simulation. I have not even entirely finished yet, so I can't not say more than that. What we are doing is comparing with the gray M1 simulation. But unfortunately, because the gray M1 is a little slower, and I hadn't expected that to be the case, it's lagging way behind the Monte Carlo simulation, so I don't have the comparison yet for you.
Okay, thank you.
But hopefully within a few months, I can at least compare to the gray M1, which will answer some of those questions, I think.
Yep, thank you.
Okay, Alessandra.
Hi, sorry for the background noise. Thanks a lot for the very nice talk. I had a couple of questions, mostly trying to see from an observational perspective of someone who does radio follow-up, a couple of things. So first thing was, you mentioned the constraints you can put on the equation of states just based on the ejecta mass. And so my first question was, does it help in any way to constrain observationally more accurately, particularly what fraction of that ejecta mass goes faster and could emit in radio rather than in optical? And then the second question was more about the unknowns in the magnetic field structure that you mentioned once the black hole plus disk forms. And so is there any observational way that one could constrain that? So what would be the observational features, if any? Is polarization, for example, anything useful? Thank you.
Okay, so for the first part, I think any observation that allows us to disentangle these components will eventually be useful. But what I'm mentioning here as well is that our current understanding of the outputs, our current models, is actually pretty limited in what it allows us to say about the properties of the binaries, right? So it would be very useful to know what actually these systems do, or how much of the matter is going faster, or is higher YE, or that kind of things. Velocity is definitely a way to disentangle some of these outflows. So having velocity information on top of what the kilonova might tell us about composition is very useful. But to actually do the full inversion using the current status of numerical simulations, that is a little beyond what we can do because of these uncertainties in the outflow masses. But that's more of an incentive, in my view, to actually push some of those simulations to because some of the uncertainties that I mentioned are things that we are now becoming capable of addressing. There's things like, especially the dynamical ejecta, I think within a few years, we should be able to run a fairly large number of simulations that have decent neutrino transport and get information about that. Yeah, I would say we are not at the point where that information would be directly usable to infer the properties of the merger, in my view. I'm very skeptical of inference that we do with current models. But I think that it's something that is possible because the properties of the ejecta do depend on the properties of the binaries. And so that's certainly something that we should look for, and maybe come back to when the model have improved a little bit in a year or two. And then for the second question, the amount of the structure of the B field. I'm not entirely sure what will solve that problem. If the simulations get good enough to predict what should happen, except for that one thing, the structure of the B field after merger, I don't entirely rule out that observations would actually tell us what that fraction is, and we have to revert from that what the B field structure should be. Or at least which ones are allowed and which ones are not. I'm not entirely sure about whether polarization would help. Honestly, having mostly worked with neutrinos and mass outflows, I haven't thought much about that part of the problem. Maybe someone else can comment on that if they have ideas. I don't know if that answers your questions.
Oh yeah, thank you very much.
Can I ask a question?
Go ahead.
I'm puzzled. Why do you expect a strong magnetic field? I mean, after all, these are two very old pulsars, and the magnetic field must have decayed a long time ago. So with all due respect to magnetic field, why do we expect?
I do not expect strong magnetic field in the pre-merger star necessarily. I do expect growth of magnetic field from the instabilities during the merger, and it can be very, very fast if you resolve a small scale structure. So I do expect large amplitude magnetic fields for small scale, on small scale. What I do not know is if that will translate into a large scale magnetic field that is necessary to drive those strong outflows. And I think, in my view, that is really an uncertainty, and I do not count on the existence of a strong, large-scale magnetic field after the merger at this point. I think that it's an important point to figure whether that can happen or not, whether there is some sort of mechanism that is going to allow us to transform these small-scale, small spatial scale but large amplitude magnetic fields into something that is more of a large-scale structure. But I would not say that that's a guarantee at this point at all. No.
Is such a process known? Is such a process known of conversion of small-scale magnetic field to large-scale ordered field?
In the disk, some of the simulations do show that. The recent simulations, I know at least the one by Sasha Chekhovskoy's group, do show some growth, even if you start from a lower amplitude field. In the neutron star core itself, I'm not aware of the growth of a large-scale magnetic field from ab initio simulation. Maybe others can comment on that if they have seen anything.
And maybe we should put this as a point for the discussion. It seems to be an interesting point.
Yes, I agree. So let's thank Francois again. Well, virtually, we cannot really all clap our hands together. And let's move to the next talk.